Hello, my name is Jean-Baptiste Tristan from Boston College, and I am presenting the paper, A Formal Proof of PAC Learnability for Decision Stumps. This is work done in collaboration with Joseph Tesserotti from Boston College, Gundinya Vaja from the University of Pittsburgh, and Anindya Banerjee from IMDEA. Our motivation is to better understand what we can prove formally about machine learning algorithms. When we think about a compiler, we know that we might want to expect a compiler to produce efficient code, or for example, that we might require the compiler to preserve the semantics of the input program. But the question that we want to ask is, what should we prove about a machine learning algorithm? Of course, there are very important properties that other people have been looking at, such as privacy, fairness, or robustness. But what we want to understand here is, are there more fundamental properties about the learning process itself, properties about learning that we could prove about a machine learning algorithm in a proof assistant? To that end, we need to understand a little bit of learning theory, and we need to understand the model of a supervised learning. We assume that there is a labeling function tau going from some domain x to 0, 1 and a distribution over x, mu. We don't know what they are, and the goal is to devise a learning algorithm or learner, which is going to take a training set, which are data points sampled from mu and labeled by tau, and a hypothesis space, which is a subset of all of the functions, all of the classification functions going from x to 0, 1. And the learner is, when we train it, chooses one of these hypotheses. Once we have such a hypothesis, we can deploy it and we can actually do classification. And if you have a new data point x, you can classify it as 0 or 1. Of course, what we would like to do is to provide some guarantee about the generalization error of such a chosen hypothesis. We would like to be able to say that based on our choice of hypothesis and based on our training set, we have some expectation that our hypothesis will behave as tau, the labeling function, the true labeling function. One of the key problems that we have is the so-called bias variance trade-off, where if we pick h too small, then it might not contain tau, or it might in fact only contain hypotheses that are really different from tau. It's a case of underfitting or bias. But we cannot choose h to be too large either, because in that case it might require a lot of training example to do a good job at choosing a hypothesis, and this is the problem of overfitting invariance. This is the type of things that we would like to prove about our learning algorithm. We would like to prove that there is a relationship between the training set size and the hypothesis class. PAC learnability and the framework of PAC learning allows us to do this. I'm only going to give an informal definition of PAC learning, and you can actually find a formal definition in the paper or in the long version of the video. We say that a hypothesis class H is probably approximately correctly learnable, or PAC learnable, if intuitively there is an algorithm. You can actually exhibit an algorithm A, which is such that for any accuracy epsilon that you might want to choose and any confidence delta that you might want to choose, if you have a training set that is big enough, then with probability at least 1 minus delta over the choice of the training set S, the hypothesis that is chosen by A, or another way to put this, the hypothesis that is returned by our algorithm A given some training set S, has an error, a generalization error of less than epsilon, right? Which is a measure, this generalization error, of how we differ from tau, the target function. Of course, again, all of this is formalized it's present formally in the paper. In this paper, indeed, we actually present a formal proof of PAC learnability. We do this for one specific class, hypothesis class, and one specific learning problem, which is the problem of learning decision stumps. We do this using the lean proof assistant, and among other things, some of the questions that drove this work were: what is the ratio of algorithmic reasoning to what I would qualify as the mathematics annoyance? That is, how much of the development is really about proving properties about the algorithm, as opposed to just proving properties about measurability of functions, events, and so on. Also, we want to better understand to what extent can we actually develop such a proof, such a formal proof, by separating the reasoning about the high-level reasoning that we find in the textbook from all of these mathematical details. The problem that we address in this paper, Decision Stumps, is fairly simple. In that problem, the domain is the real line, and the target function tau can simply be associated with a point on the real line, such that any value less than tau is a blue circle, anything bigger is a red cross. The first question is, what set of hypotheses should we consider? We could consider any function from R to 0, 1, or to a blue circle and red cross. But here we'll just simply consider the set of all of the functions which are such that which are given by some value on the real line, and which will classify anything as blue circle if they're less than that, and red cross if they're more than that. And so we identified our hypothesis class as simply being R, all of the points on R. An algorithm, then, to show that this hypothesis class is PAC learnable, could simply be the algorithm that returns the largest blue circle. Our proof is organized in 4 different parts. One part of the proof has to do with the algorithm implementation. It's only 20 lines, and I think it's fair to say that it is trivial. And the algorithm is deterministic, but its input is random, and so for that reason we actually use the jury monad to specify the algorithm in the Lean Proof Assistant. We have to prove the algorithm properties, which is about 150 lines, which is also fairly trivial and in a sense correspond to proving that the algorithm indeed returns the rightmost blue point. Finally, all of the measurability analysis results that would usually not appear in a textbook proof correspond to Naharian lines, and they are actually more difficult. Some of them are really non-trivial, and that includes proving that the algorithm is a measurable function, that the events are measurable sets, but also proving that some of the things that are glossed over in proofs, such as the fact that there exist some specific points on the real line, actually hold. And finally, the final part of the development is the probabilistic statement and the high-level reasoning. It's about 500 lines of proof, and it's basically routine probabilistic reasoning that correspond very closely to what you would find in a textbook proof. And to a large extent, this amounts to proving that the algorithmic properties lead to the set properties over events, which themselves lead to some probabilistic properties. So, aside from giving a better idea of what are the different parts of the proof and where most of the difficulty lies, where unfortunately much of the difficulty lies in the mathematics details that we do not actually, that we gloss over on a paper proof. The modularity is so that we were able to define the algorithm and its properties in isolation from all of the measurability and analytic results. The probabilistic reasoning and the statement are actually built on these two things, on the algorithm definition properties and on the measurability and analytic results. And of course, the proof depends heavily on the algorithm definition, but we can actually have enough automation so that the measurability details do not actually encumber the probabilistic reasoning. In conclusion, you can find all the details about this proof in the paper. There is also a documented proof on my GitHub repository. And finally, I should say that working with Lean was a very positive experience, in large part because MathLib is a very nice project and actually gave us all of the results that we needed to do our proof. Thank you very much.